In this example, we're going to look at how to use the method of Lagrange multipliers to find the extreme values of a function. In particular, we're going to look at how to use this method to find the minimum value of the function f of x and y equal to x squared plus y squared, subject to the constraint that g of x and y, which is equal to x squared minus y squared, must be equal to 4. So how does this method work? Well, as we show in the notes, the basic idea is that a function will attain an extreme value subject to a particular constraint when the gradient of the function is proportional to the gradient of the constraint. That is, the gradient of f is going to be equal to some constant times the gradient of g here. We call this constant a Lagrange multiplier. We'll have one Lagrange multiplier for each constraint we have. Here we only have one constraint, so only one Lagrange multiplier. But in other problems, it's important to keep in mind, you may have to introduce more than one of these. Typically, when there's only one, we use the Greek letter lambda for our Lagrange multiplier. So this equation, if we write it in component form, gives us partial derivative of f with respect to x is 2x, partial derivative of f with respect to y is 2y, and then that's equal to lambda times partial of g with respect to x times partial of g with respect to y. It's minus 2y. In other words, it gives us two equations. 2x is equal to 2x lambda, and 2y is equal to minus 2y lambda. Let's call those equation 1 and equation 2. Our goal is to solve for x and y, but we don't know what lambda is, so we actually have three unknowns here and only two equations. But it's important to keep in mind that our constraint equation up here acts as a third equation, which will eventually help us fix the values of x, y, and lambda. Let's now try and find values of x, y, and lambda that satisfy these equations. Looking at the first equation, we can see that this will be satisfied two ways. Either x is going to be equal to 0, or lambda is going to be equal to 1. Now if x is equal to 0, then looking back at our constraint equation, we get minus y squared is equal to 4. And there's no solution to that equation. There's no value of y such that minus y squared is equal to 4. So this has no solutions. In other words, this equation, along with our constraint equation, require that lambda be equal to 1. So we'll try this in equation 2. So plugging lambda equals 1 into equation 2 gives us 2y is equal to minus 2y. The only way to satisfy this is to have y equal to 0. You might start to think we're running into the same problem we had a moment ago with x being equal to 0, but having y equal to 0 is allowed, right? The constraint equation, equation 3, would now say with y equal to 0 that x squared is equal to 4. And that has solutions. That's just x equal to plus or minus 2. So that's it. The method of Lagrange multipliers then has yielded two critical points, minus 2 and 0, and 2 and 0. And both with Lagrange multiplier lambda equal to 1. Since we want to know the minimum value of the function itself, not just what the critical points are, we should plug these x and y values into f, and whether that's plus or minus 2, we'll still get plus or minus 2 squared is just going to give us 4. So that's the minimum value of our function f, subject to that constraint. So we're done the problem now. With a bit of thought, we can see that this result actually makes sense. So what are we doing here? We're looking at this function f of x and y is equal to x squared plus y squared. The graph of this function is a paraboloid, and its level curves are circles. So we're basically asking what's the smallest radius circle we can have if our x and y coordinates must satisfy x squared minus y squared equals 4. But the equation x squared minus y squared is equal to 4 corresponds to a hyperbola. So if we wanted to sketch this problem, what we'd be looking at is basically saying, consider the level curves of the function f, These are a bunch of circles. And now find the smallest possible circle that has x and y values sitting on the hyperbola x squared minus y squared is equal to 4. Well, that hyperbola looks something like this. And it has x-intercepts 2 and minus 2. And so if we're looking for the smallest circle, the level curve with the smallest radius that intersects this hyperbola, it would be this one here that intersects right here with radius 2. And sure enough, everywhere on that curve, the function has value 4, which is what we found above. Alright, so that's all I wanted to do in this example, was walk you through the process of using the method of Lagrange multipliers with a relatively simple function and constraint, and give you some geometrical insight into how it works. But I'll stop there. Thanks.